Solving logarithm equations with common bases is going to be very similar to what we did with solving using common bases of exponentials. However, we have a slightly different key concept. And what we see down here is we have on both sides of the equation log base b. If we have log base b on both sides of the equation, yet they're evaluating something different, what we know must be true then is x must be equal to y. This will be a very helpful concept for us because now what you see is upon moving from the original equation to just simply x equals y, we no longer have a logarithm which we need to evaluate, and will result in, for us, a pretty basic algebraic equation to solve. So let's go ahead and take a look at our first example. Now you'll see in the directions what we're asked to do is it says solve the equation, but it also says check for extraneous solutions. Alright, so the extraneous solutions are going to result if we come up with a value of x such that upon substituting it in, the expression for which we're evaluating the logarithm, if either one of those is negative, then our answer will be an extraneous solution. So that's the one look for that we've got to be careful of in this section. Alright, so let's go ahead and if we take a look at the first example, we see we have the natural log of 7x minus 4 and natural log of 2x plus 11. Therefore, what this is saying is since we have the same base for the logarithm, we could just take what they're evaluating, 7x minus 4, 2x plus 11, and set those two statements equal to each other. Now, as we stated before, we have a pretty basic equation. I'm going to go ahead and subtract 2x to both sides, add 4, and then divide both sides by 5, and that gives me x equals 3. Now, I am going to want to check, and I'm going to take this value and substitute in for x to make sure that the portion inside the parentheses is positive. So 7 times 3 is 21 minus 4 gives us 18, so we're good there. And we see that 2 times 3 is going to be positive, plus a positive will be positive, so we're good there. So therefore, x equals 3 is a solution to our statement. Now in the second equation, we see that again, it's nice for us because I have log base 4 on the left, log base 4 on the right side of the equation. Therefore, what I'm evaluating, I can set equal to each other. 14 minus 5x equals 3x minus 10. And in this case, I'm going to add the 5x to both sides to give me 8x, and then add 10 to give me 24, and I get x equals 3. Now, again, don't think that all the time we're going to get an answer of x equals 3. That's just pure coincidence. However, we need to check to see if that's an extraneous solution. So what I'm going to do is I'm going to go ahead and again substitute this value of 3 in for the x. But look what happens in this case. When I substitute 3 in for the x, 5 times 3 is 15, and 14 minus 15 is a negative 1. So since what I'm evaluating the logarithm of is equal to a negative, this x equals 3 does not satisfy the original equation. Therefore, we're going to actually label this an extraneous solution. So that's one thing that you're going to want to check for whenever you're solving here. The process is very similar. We're going to end up with nice basic algebraic, most of the time linear algebraic equations to solve, but double check for